Hi students, tonight we're going to talk about formal charge and resonance, and so we're going to dive a little bit more into some of those structures and the structural formulas that we talked about in our previous videos. And of course, as always in chemistry, it always can be a little bit more complicated, and that's what formal charge and resonance are then going to be about. So essentially what formal charge is that in a charged molecule or ion, sometimes we really kind of need to know where the charge is, just like before we kind of need to be able to see where is the polarity of the molecule. And actually, importantly, this doesn't just have to happen in charged molecules. We can also use the mechanism of finding the formal charge to help us figure out what is the correct structure, because as you guys know, sometimes when you put those structures together, it's hard to tell which one is right because you have a couple of possibilities, so which one is the more likely one. And sometimes formal charge can help us to do that as well, although a lot of times we'll also rely on some oxidation number stuff, and those are two sort of competing systems. So the way that we find formal charge, so say we've got an ion here. Of course, this is a polyatomic ion. You might recognize this from Chem 1 as a hydronium ion. Essentially, that's what acids produce. They give off protons, H+, and those are going to join with water molecules to form H3O+, and we call that H3O+ a hydronium ion. So this is its structure. And in fact, to actually make this perfectly correct, we would actually put a plus charge outside of the brackets. So a couple of quick things to note here. Whenever you draw a polyatomic ion, you usually want to go ahead and put it in brackets and then put the charge outside of it. That's just sort of the normal mechanism for doing that. So when we're calculating formal charge, what we're trying to do then is we're trying to find what is the charge on each individual atom. So like, where does the charge actually sit? We know there's an overall +1 charge, but where exactly is that +1? Is it here, 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 or here? There are 4 places that it could be because there are 4 atoms there. So the way we calculate formal charge is, and this looks really complicated, but it actually works out really simply. We'll talk about it here, and then of course we'll work a bunch in class as usual. And the way that you find formal charge is you take the normal valence electrons that that atom would have if it wasn't in a compound, okay? And then you're going to subtract from that the sum of your unshared electrons, okay? So in other words, electrons that aren't in a bond, okay? So like these guys, these are not in a bond, okay? Plus half of the shared electrons. So basically what that means is that every bond is going to count for 1 instead of for 2 electrons, because we're saying that they're shared. And so the implication here in formal charge is that they're being shared equally, so that the 2 atoms in the bond each get 1 of the electrons. We know that that's not actually true, and that's why a lot of people would argue that we want to use oxidation numbers instead, because oxidation numbers are going to sort of more clearly state, more clearly take into account the electronegativity differences. But for our purposes right now, for doing formal charge, we're going to go ahead and work the formal charge for this particular molecule, or this particular ion. So we'll start with the hydrogens. Okay, so for each hydrogen, every hydrogen here is bonded to an oxygen, and that kind of makes it convenient because that means we can just calculate it once and then figure out, we'll know it for all of them. So the formal charge is going to be equal to the valence electrons. So how many valence electrons does hydrogen normally have? It normally has 1. Okay, and then we're going to subtract the unshared electrons, and if you look at these, there are no unshared electrons, right? And hydrogen shouldn't have any. Hydrogen's full with just 2. Okay, so there's 0 unshared electrons plus half of the shared electrons. So each one of these hydrogens has 1 bond. Okay, so that would be 2 shared electrons. Remember, a bond is 2 electrons, and so half of that would be 1. And so essentially this comes down to 1 minus 0 plus 1, or 1 minus 1. And so hydrogen is going to have 0. So that what that tells us sort of immediately is that the charge isn't on any one of the hydrogens. Now, even without doing more calculations, we could sort of immediately tell it's on the oxygen, but let's go ahead and calculate the oxygen. So the oxygen, its formal charge is equal to the number of valence electrons that it normally has, which would be 6, okay, minus its unshared electrons. And how many of those are there? There are 2 right there, so that's 2, plus half of its shared electrons, or you could also state that and just say, or plus the number of bonds. So in this case, it would be 1, 2, 3, okay? So there's 6 shared electrons, half of that would be 3. So 6 minus 2 plus 3, or 6 minus 5, that means that the oxygen has a +1. In other words, that is then going to tell us that if we're looking for the formal charge, that actually where the charge resides in this molecule is on the oxygen. Okay? The hydrogens all have a formal charge of 0. The oxygen has a formal charge of +1. Okay? So that's how we calculate formal charge. Now, formal charge and the idea that sometimes the bonds and the structures are a little bit more complicated than we normally think can lead us to some more complicated structures and what we call resonance structures. Resonance structures essentially mean that there's not really one good way to draw it, that actually we would have to draw it several ways or a couple of ways at least, and then that the way it really is in the real world would sort of be a blend of those two things. So let's just take a real quick example here and let's work through a carbonate ion. Okay, so carbon, 4 valence electrons, right? Oxygen has 6. We've got 3 oxygens here. You'll note that I'm not really following the exact convention when I set up my electrons, and that's obviously because I kind of know where I'm going to need them to go bonding. So this is the electrons that I would normally have. So remember that this 2 minus here actually means that I have 2 extra electrons. And I'll add those in after I bond. Whenever you get a charge there, that either means if it's positive, you take an electron out of that polyatomic, or if it's negative, you've added in somewhere. So we're going to add these 2 in, and we'll talk about where we're going to add them in here in a second. So let's go ahead and draw our bonds. As always, the easiest way is to just sort of say, okay, I'm going to bond some of the single stuff together. Okay, so that works out. That was pretty easy. And then, obviously, no one's happy yet. Everyone's got 7, so I'm going to need to do some more bonding. So if I draw another bond here between these 2 singles, in other words, a double bond here, that actually makes the carbon happy. It also makes this oxygen happy. But what about these 2? Well, they're not happy, but remember, I've got these guys up here, okay, and that's not a smiley face. And so that means I've got 2 more electrons to put in. So if I put 1 on this oxygen and then 1 on this oxygen, everyone now has 8, and if we sort of clean that up a little bit, that would look like this. Okay, so oxygen, and I'm going to change sort of where my oxygens are to sort of better represent the molecular geometry, and we'll talk a little bit more about that later. But remember, molecular geometry would be what's the shape of the molecule, and so I'm just going to draw that now, and we'll explain why that is a little bit later. So this is what I now have. I have everyone has 8, and everyone's pretty happy. But, you know what? In reality, that double bond didn't have to be there. What? Couldn't it have been there? Couldn't it have been there? And in fact, that's exactly the case. If we really drew the structure, what we would have is that there are 3 different possibilities for where we could have put that double bond. So this is the one that we drew in the previous page. And then the double bond also could have been here, or the double bond could have been up here. And in reality, we would say that any one of those 3 structures could be what the structure is, but in reality, how do we know which one's which? Formal charge won't really help us in this case. It would just sort of switch which oxygen has the charge, okay, so that's not really going to help us a lot. And what we actually find in reality is that it's really a blend of these, okay? If any of these 3 was true in the real world, what we would see is that this bond is going to be shorter than these 2 bonds, and that's not actually what we see when we do testing on this ion. What we actually see is that all the bonds are equal. So what that means is in your mind, you sort of want to think, okay, I'm going to take these 3 things, and I'm going to sort of squash them all together. And if I squash them all together, kind of looks something like this. And what this represents is that I've got a bond between each of the carbon and oxygens, okay? And then the dotted lines here represent and say that this is a partial bond. In carbonate's case, that would mean that essentially that partial bond is like a 3rd bond. And so each carbon-oxygen there, instead of 1 being a double and 2 being a single, what the reality of it is kind of like every one of them is a 1 1/3 length bond. And so sometimes we'll represent it like this. The vast bulk of the time, though, when you're required to draw resonance structures, this is what you're going to draw. You're going to draw each individual case and what it can be. That seems like it might be really tedious, but sometimes there's only 2. Sometimes there's more than that, and quite often there are 3. And really, there are lots of ways you can do it. You could draw them out and try to figure it out all individually. I think one of the easiest ways is that if you have a situation like this where you've got a double bond here and you've got similar atoms over here, then the easiest way to draw the resonance is just to assume, well, I could move the double bond to other places. Okay? And that idea of being able to move the stuff or being able to move the electrons, that also leads us into what we call curved arrow formalism or arrow formalism. And all that means is that we're going to draw arrows to show where the electrons move as we sort of shift from place to place here. Okay, and again, remember, this is a model. It's not a completely apt illustration since these are sort of 1 and the 3rd bonds. But we're going to illustrate it under these 3 resonance structures. Where do the electrons go? So if we draw the arrows here to show this, what we would do is going from this structure here to this one, okay, these 2 electrons moved here to form the double bond, okay, and then these 2 double bond electrons move over to this oxygen to form that, okay. So that's basically, these curved arrows are going to show us where the electrons are going to move to. If we looked at the next case, okay, or where are our next set of arrows? They are going to be, so our next set of arrows are going to be right here, okay? And again, we're showing as I move from left to right, from here over to here, what happens? Well, in this case, we're going to say, okay, we're going to put those electrons back over here. Then we're going to take this pair, and that's going to come down and form the double bond here that we get over here. So we went from here, okay, to form here, and then these moved over to form this particular model. And then, of course, what would really happen is we've got to draw some curved arrows over here to represent what would happen if it goes back over to this side. Okay, and so in that case, what happens is that these electrons move back to form that double bond moves back over there, and then we get this case over here. So that's what we would use those curved arrows for. There are actually a couple of ways that we can use the curved arrows. The way that we use them here says, hey, this is how a pair of electrons is moving from one place to another. We'll use this in resonance. We can also use it in reactions as well. We'll do some of that later in the year when we start talking about some of the organic reactions. We can also draw half-headed arrows, and if you're like, what the heck is a half-headed arrow? They're called fish hooks, but basically I draw a curved arrow with just one side on it. Looks kind of like a fish hook. And that would represent, instead of a pair of electrons, that would represent one single electron moving from one place to another. So as we talk about radicals and stuff like that later, that single-headed arrow, those fish hooks, will be important. And while we're talking about arrows, a couple of other important arrows here are that you'll notice that in all of the resonance structures that we drew these double-headed arrows. Double-headed arrows represent resonance structures. If you've got double-headed arrows, that means that there's more than one structure here that is essentially equivalent. And so that's how we're going to indicate resonance. Note that that is not the same thing as us drawing double-headed arrows or 2 arrows going in the opposite direction that would represent a reversible reaction when we get later on and we're talking about those kinds of reactions. So that's a different thing. So double-headed arrow means resonance. Single-headed curved arrows means pair of electrons moving somewhere. And then a half curved arrow, a fish hook, represents one single electron moving from one place to another. All right, guys, hope that helped. And again, as always, we'll spend a fair amount of time in class running through these, practicing them, comparing them with each other, and making sure that everybody's got a good handle on formal charge and resonance and curved arrow formalism.